So welcome all to next edition of Go Seminar. Today we have our own Ondřej Suchý talking about Directed Traveling Salesman Problem.
Okay, thank you for inviting me and introducing me. Okay, so this is a joint work with Vašek Blažej, who is our former PhD student, and he was in Warsaw when we were working on that, but as I've just heard, he's these days leaving to industry. Then it's a joint work with Andreas Emil Feldman, who was in Sheffield, but now he is in industry. And then it was a joint work with Fibos from our department and with Pavel Žaževský, who is hopefully still in Warsaw University. And so let me give you some motivation for what is traveling salesperson problem about. So suppose you are having a delivery. So this is my favorite city. Suppose you are having some delivery service and you're trying to find an order in which you should deliver some packages in order to spend as few time on that as possible. And if you are working in a city center of a big city like this, then probably most of the streets are one way, and maybe the travel times also differ, like whether you're going this direction or that direction. So this motivates taking a directed graph. Okay, so yeah, if you want to be staring to this very nice city a little longer, so it is definitely like I'm not as good operator of these tools as I could be, and yeah. Okay, so this is a formal definition. So our input is a directed graph with edge weights, and we are also given some budget. And the question is whether there is a closed directed walk of total weight at most budget. And I would like to stress that it should traverse each vertex at least once, not exactly, just at least once. Like I want to get to every position where I should deliver something. So, for example, there is an example of a graph with edge weights, and if I was thinking about it long enough, I think this is an optimal solution for this graph. And you can see that this edge is used twice, and these vertices are visited twice. So yeah, it might be necessary. I think this is definitely necessary for this graph to visit this vertex several times. Okay. So we will also study a bit more general problem, which is called directed waypoint routing. And apart from the things that we were given already before, we are also given a set of waypoints or terminals, if you wish, and we are also given edge capacities. And now the task is again to find a closed directed walk of total weight at most b that traverses every vertex, every waypoint, every vertex in W, and such that it traverses each edge at most its capacity times. Yeah, we shouldn't use any edge more times than its capacity. Okay. So what can be shown is that every vertex, and therefore every edge, is traversed at most the number of terminals times, because otherwise we could use different solution which satisfies that. And as a corollary, we can show that this problem is definitely more general than the previous one. We can phrase the instance of directed TSP as an instance of directed waypoint routing. Okay. So what is known about this problem? So directed TSP is NP-hard even in cubic graphs, and even if we insist on each vertex being visited exactly once. Okay. It's not yeah, doesn't matter. It's known to be solvable in something like 2 to the n times n squared by a famous Held-Karp dynamic programming, which was invented also by Bellman. And maybe it's also famous that quite recently, like some 4 years ago, it was shown to have constant factor approximation. Note that like the since we allow each vertex to be traversed more times, the triangle inequality is somehow implicitly present to the definition of our problem. Okay, so concerning parameterized results, it's somehow folklore result that if you insist on each vertex being visited exactly once, then you can solve it in FPT time with respect to treewidth. And Marx and his colleagues some 10 years ago showed that this problem is W1 hard with respect to pathwidth. So we cannot hope to have like this variant where we allow more visits to a vertex. And quite surprisingly, so this is all from parameterized setting, but quite surprisingly, there are 3 results on parameterized approximation. So that's quite non-typical for problems, not to be studied from parameterized perspective, but being studied from parameterized approximation perspective. So what is our approach? So we study parameterized complexity. I hope that I don't have to explain what is FPT, XP, and W1 hardness, but maybe there is some student that is not so familiar with this. I hope it's understandable from the slides. So more importantly, we study the complexity of these problems with respect to structural parameters, and we consider structural parameters of the underlying undirected graph. So we use undirected parameters and always consider the undirected underlying graph as having this parameter. Okay. So some examples of parameters we have already seen: treewidth, pathwidth. We will also use feedback edge number, which is the minimum number of edges that you have to remove so that you obtain a forest. Some further parameters that we will use, if I speak about, if I have some class C and speak about distance to C, it means the minimum number of vertices that I have to remove from my graph to achieve property C. So like an example, vertex cover number is the distance to edgeless graph, like the minimum number of vertices I have to remove such that no edges remain. Okay. On a similar note, vertex integrity is the minimum k such that there is a set of k vertices that I can remove such that every remaining component, weakly connected if you will, has at most k vertices. Okay. So it's like now k plays 2 roles, like size of the modulator and size of the connected components after removing the modulator. And I will also speak about treedepth, and if I was to define it quickly, then you can define that for, and I will actually use this definition if I would use some. So if you have one vertex graph, then it has treewidth 1. If you have a disconnected graph, then the treedepth is maximum over connected components. And if you have a connected graph which has at least 2 vertices, then you just try to delete vertices one by one, look on the treedepth of the remaining graph, take the minimum, and add 1 for the deleted vertex. Okay. So what are our results? First of all, for directed waypoint routing, because of these capacities of edges, this help card dynamic programming doesn't apply directly. So it's not that clear that it can be solved in FPT time with respect to size of the solution. So we got this result again, showing that it can be solved in something like 2 to the O of k times m log m, where m is the number of edges. Then we have had a look on feedback edge number, and there we show that it's, and I will show you this algorithm. It's your advantage over the Isaac people, because I added that recently. And then we show that it is FPT with respect to vertex integrity although the running time might look scary, it's something like k to k to 6. But okay, it's FPT. And then there is the algorithm based on treewidth and the number of visits. And it's FPT with respect to treewidth and the number of visits. And this shows that it is XP with respect to treewidth. And also because of this lemma, since we know that the number of visits is bounded by the number of terminals or waypoints, we also get that this is FPT with respect to treewidth and the number of waypoints. So, yeah, I will not show that. And finally, to complement these positive results, we also showed that directed waypoint routing is W1 hard with respect to treewidth, even in unweighted graphs. Treedepth, sorry. Treedepth. Yes, treedepth. So let me note that for the positive results, having the result for directed waypoint routing strictly generalizes having this result for directed TSP. But for the hardness, it makes it somewhat weaker. Okay. But all our results are for directed waypoint routing. Okay, so let me show you the picture. So this is like a Hasse diagram of structural parameters, obviously with vertex cover on top. And so this was known before we came to the problem. So it was known that it is in XP with respect to treewidth, and that it is W1 hard with respect to pathwidth. So what I promised you to show is that it's FPT with respect to vertex integrity and with respect to feedback edge set number. So obviously this implies that it is also FPT with respect to vertex cover because it's bounded by vertex integrity. And we also show that it is hard with respect to treedepth, although only for the directed waypoint routing. Well, there is still some space in the middle where we can put distance to constant pathwidth. And if you really analyze like what Marx and his colleagues showed concerning pathwidth, it shows that it's actually hard with respect to distance to constant pathwidth. It's something like 3 or 4, depending what exactly result you're heading for. And yeah, we can also show that our hardness holds for distance to constant treedepth. And I will give you the constant at the end of the talk, right? Okay. So let me present some of the results. So let me start with the FPT algorithm with respect to feedback edge number. So first we apply some reduction rule, which simplifies the instance, and it basically gets rid of vertices of degree 1. Since I don't want to like talk about whether it's in degree, out degree, or whatever, so it's vertices which have degree 1 in the underlying undirected graph, meaning that they have only one neighbor. So the easiest option is, if that vertex is not a waypoint, then we can just forget it, remove it from the graph, and pretend it was never there. And if it is a waypoint, but one of the edges necessary to get there and back is not present, then there is no way to visit this waypoint. And finally, if there is a way to visit this waypoint, we simply like count the 2 edges that are necessary to visit it, subtract them from the budget, and make its neighbor a waypoint, because you have to get to the neighbor. Okay, after that, each vertex has degree at least 2, again, in the underlying undirected graph. Okay, so what is the structure of the graph? So we have a feedback edge set of size at most k of the underlying undirected graph. If we remove this set of edges from the graph, we get a forest. And if we take the vertex set of these removed edges, let's call it R, then we have that this vertex set contains at most 2k vertices. Well, it's a forest, but in the whole graph, every vertex has degree at least 2. So all the leaves of this forest must be in the set R, meaning that we have at most 2k leaves. And if we have a forest with at most 2k leaves, it also has at most 2k internal vertices of degree at least 3. So to sum up, we have at most 4k interesting vertices, and it's also easy to see that we have at most 5k paths that connect these interesting vertices. Right, for 4k of them within the forest, and this extra F edges, which are at most k. Okay, so let me deal with the paths. So if we have a path, we guess how is this path used by a solution. So one option to use the path is just to traverse it from left to right, or for you, left to right. And then we can traverse it from right to left, both directions, or we can go from one end, go to somewhere, then turn around and go back and never visit it from the other side, symmetrically from the other side, or we can go from both endpoints to some middle and then turn around and go back. So we guess for every path which of these options will the solution take, and then do some replacement. So the last option is that this path is not used at all by the solution. Okay, so and then we do some replacement. So we always put there just one vertex or 2 vertices in some cases, and this one terminal forces that this traversal is done of the path, and it's not possible to do anything else basically. Although in the third case you can do something more. We set the capacities and weights appropriately so that this traversal costs as it should cost. And in this middle 3 cases, we also set one of the endpoints or both of them to be terminals, so that we know that we will be able to approach this path from this direction. Yeah, and this means for every path we will have constant number of vertices. So at the end, yeah, and if here we are removing the path and we pay the amount that is necessary to visit all the terminals on that path, the cheapest way. Okay, so and some of these options might not be available for our graph, but that's a standard thing to treat. So after that, we have constant number of vertices on each path. So we are creating something like 7 to 5k instances. For each of them, we have only linear number of vertices, linear in k, linear number of edges, and such an instance can be solved by brute force in k to the OK time. So in total, we get the time as claimed, k to the O of k plus sample limit to find the path. Okay. So this was the algorithm with respect to feedback edge number. So now let me switch to the more interesting one, the FPT algorithm with respect to vertex integrity. So let me recall, we have a modulator of size at most k, such that each connected component of the rest of the graph has at most k vertices. And the first thing I want to define is the notion of a segment. A segment is a walk with at least 2 vertices that starts and ends in M, and all the internal vertices are not in M. So I have some examples here. So this is a walk, this is a segment. It starts in M, goes to some component and ends in M. It can also look like this, but it can also look like this, where this edge is used twice. And it can also look like this. This is also a valid segment. Okay. So having a segment, we can talk about traversals. So what is a traversal of a component? So it's an inclusion-wise minimal collection of segments, and each of the segments should be should be shortening wise minimal, meaning that I cannot shorten it without like leaving some vertex uncovered. It covers every waypoint in the component C and respects the capacities. Okay, so this is one possible traversal of this component. It covers here the terminals are like, okay, yeah, I'm inconsistent in denoting terminals. Okay, and there is a claim that is important for us. So sum of lengths of the segments that compose a traversal is something like at most k squared or something like that. So there are at most k to k squared possible traversals for each component. And with this in hand, we can give an overview of the algorithm. So first of all, the algorithm guesses which kinds of segments it will use at all. So this is a directed graph on the set of vertices of the modulator, and there is an edge uv if there should be a segment from u to v used by the solution. And we call a segment bad if it's not supposed to be used. We call a traversal bad if it contains a bad segment. And we call it good if it's not bad. Okay. So we have some requirements on this graph H. So it has to be strongly connected, and it should contain all the waypoints that appear in the modulator. So all of them will be visited. And if this is not the case, we just reject the guess and continue with another guess. And once we are done with that, we construct some ILP, file structure, which will determine for us how many times we should use each element of the solution, what exactly we should use, and how many times we should use it to obtain a solution. So how does this ILP look like? So we have some variables, how many times the element is used. We have a 0, 1 variable for each good traversal of each component. And we have a variable ranging from 0 to n for each good segment, which is a path. These will be some extra paths that we add to the solution to balance it or to make it connected or something like that. So this is like an extra path that we can add to the solution. And our aim is to minimize the total weight of the elements that we use. Okay. So what are the constraints? For each connected component, we select exactly one traversal. Each edge is used at most as many times as its capacity. And each vertex in the modulator is balanced, meaning that there is as many segments leaving it as there are segments going to it to create some Eulerian graph. And there is at least one segment realizing every edge of the guessed graph H. And now I want to convince you that this ILP has a nice structure. What does it mean to have nice structure? We will aim for n-fold ILP. And I claim that there are only k-squared global constraints. So which constraints are global? Those are these that each vertex in the modulator is balanced, and that at least one segment from each for each edge is used. And then there are constraints which are local for each component, meaning that they only appear in constraints that concern this component. And it's that exactly one traversal is selected for this component. That's one local constraint, and another local constraint is that the edges that are incident on this component are used at most as many times as they should be. So once we know that, we use big hammer, which tells us that such an ILP can be solved in this running time. Okay. Ask Dusan if you want to get this explained. Okay. So the last part I want to show you is the hardness. So we will reduce from the problem that is called capacitated dominating set. In capacitated dominating set, we are given an undirected graph and some capacity function on the vertices and some positive integer k, so some budget. And the question is whether you can select a set of vertices which is a capacitated dominating set, and of course this set should be of size at most k. And what does it mean to be capacitated dominating set? It means that there is a mapping for every vertex that is not in the set. It will select its dominator, like which vertex should dominate it, and at most as many vertices should select this particular vertex in the dominating set as its capacity. I mean, the vertex has a capacity for how many vertices it can dominate, and yeah, you should assign the vertices outside the dominating set to such vertices such that the capacities are satisfied. Okay, so in this case, this green thingy is a capacitated dominating set because there are ways to assign the other vertices to these vertices without like fulfilling the capacities. If you select this vertex set, although it is a dominating set in the standard sense, it's not a capacitated dominating set because the capacities do not suffice to cover the vertices outside. And for this problem, it's known that it is W1 hard even with respect to distance to stars, the minimum number of vertices that you have to delete from your graph to obtain disjoint union of stars. And this is due to Dom and his colleague 2008. Okay, so how will our reduction look like? So almost all capacities in the graph will be n, meaning no restriction on capacity of this edge, with very few exceptions. And all the weights will be 1, no exceptions. And to get from a terminal to terminal, we always have to traverse a path with 2 internal vertices or with 3 edges. And the budget will be set to 3 times the number of waypoints, meaning that every waypoint is visited exactly once. Yeah, there is no way to do it anyhow differently. So an example of a gadget is this one. This in and out just means that all the edges are coming, like all the edges that are not part of the gadget are coming into this vertex, and this out means that all the edges are going out. And this gadget has to be traversed exactly five times because there are five waypoints within the gadget. Each of them has to be traversed. So yeah, we will use this thing. We wouldn't even have to put this capacity here, but let's put it there. Okay, a crucial part of the reduction is this cover gadget, which is inspired by Fomin and his colleagues. So in this gadget, we will always traverse this gadget from S to T, right? And we will be always able to do it. There will be always a path going to S and a path going out of T. Just sometimes we will be also able to reach X and to get out of Y. In this case, we can use a different path through this gadget, which looks something like this. If we are able to reach X and Y, then we can use this blue path, which notably also covers Z. Right? So This path didn't cover that, but covered all the waypoints. This path covers that. But for that, we have to be able to reach X. So this is a schematic depiction of this gadget. So we always will go from S to T, and sometimes we go from X to Y, via Z. Okay. So now with that in hand, we can present the reduction. So for every vertex of the original graph, there will be a vertex ZV, which represents this vertex being dominated. So if we select some vertex U into a solution like this one, then first off, it means we come through X, we will be able to dominate is ZU, and once we leave from Y, there are these gadgets for the neighbors connected to that, and we can use up to CU of them, where CU is the capacity of U for dominating. So we will always go through X here, dominate this, go back, and maybe now there is no more capacity on this edge, so we can dominate anything more. So I hope that with this you're ready for the overview of the whole construction. So there is like a selection part on top right. It's top left for you. This is like a selection gadget, and from this one you can go and select some vertices to be part of the dominating set. You can select at most k of them because that's the number of times we traverse this gadget. Then they can dominate something else, and then there is this auxiliary part which does all these S to T traversals. Like for every gadget, it will traverse it once from S to T. Like doing this like garbage collection or whatever you want to call it. Well, actually, there is one more traversal of both, which creates this connection so that the construction is connected. Okay. Yes. So this was the construction. Now I promised to show you the constant. So if we started with some m such that G minus m is a disjoint union of stars, then in this new graph, there is a modulator of size 7m plus 7 to treedepth 86. And it's mainly because of this cover Z gadget being so big. This is this 86. You know?
What do you mean by treedepth 86? Oh, it's the distance to 3. Wait.
Yes. This 7n plus 7 is the distance to treedepth 86.
Which is constant.
Which is constant. Okay. Yeah. To a constant treedepth, if you will. So what was our contribution? We showed that directed waypoint routing is FPT with respect to the solution size, number of edge occurrences, with respect to feedback edge number, with respect to vertex integrity. It is XP with respect to treewidth, FPT with respect to treewidth combined with the number of visits, and FPT with respect to treewidth combined with the number of waypoints. And it's W1 hard with respect to distance to treedepth 86 in unweighted graphs. So what is left? So open problems. The main open problem is what happens with respect to feedback vertex number or distance to treewidth 1, if you will. Another open problems, what happens with respect to distance to disjoint paths? Pathwidth equals 1, if you will. And what happens with respect to distance to stars, which is treedepth equals to 2. Okay, another question is this reduction and the reduction of Marx, both of them use vertices of large degree. So the question is, can we show an FPT algorithm with respect to treewidth combined with the maximum degree? We don't know. So yeah, thank you for your attention.
Time for questions. I have one.
Yes.
Is there anything known about when you also parameterize by the capacities, by the edge capacities? Or is that somehow covered by the previous things?
Not really, I would say. Not really. So the result of Marx is directed TSP, not for.
Right. Yeah.
This doesn't mean capacities one; it means unbounded capacities. But yeah, and not that from top of my head I would be able to say that like bounding the maximum capacity would help you in any direction. I would rather say that you can somehow simulate large capacities based on gadgets. So I wouldn't expect that. Yes.
What about
Kernels? We didn't go into kernels. So yeah, this is also open.
What about bounded edge weights, or like maybe even constant edge weights?
Well, so our hardness is for unweighted graphs, and yeah, the hardness of Marx is also for unweighted graphs. Then you have to increase the pathwidth by one, but something. But yeah, so this doesn't seem to help bounding the weights.
More questions? Well, if not, then let's thank Ondřej again.